Now we'll switch gears. We'll go into the domain of X-rays, which will be with us for the next, for this second part of the week of this lecture. The next week's lecture, we'll talk about X-rays interactions. Then we'll talk about computed tomography, and the following weeks are emission computed tomography. Now, X-rays are the beginnings of biomedical imaging. Do you recognize this image? This is actually taken in 1895 by Wilhelm Conrad Röntgen, and it is the hand of his wife. You can see here in the image, you can see the wedding band of his wife. So this is Wilhelm Conrad Röntgen, and it is actually quite befitting. He received the Nobel Prize in Physics, the first Nobel Prize in Physics in 1901. And the first Nobel Prize in Physics, I find this remarkable, that this was given to the father of biomedical imaging, Wilhelm Röntgen. The lab that he's taken these images in, this image here on the top, this is his lab where he did the development of the X-rays, detection of the X-rays and the imaging. Now, if we look at this video here, this is taken from the Museum of Modern Art in San Francisco. It's actually more on the arts. I find it remarkable, the images that you see here. We'll start out with the image from Röntgen's wife. Then we'll see a more modern X-ray image at higher resolution. We can see the image of animals, of a fish, and of an embryo. I think this is a embryo of a chicken. And finally, do you recognize the last image? Look at this image as we zoom through it. And as we go through it, you can also see here at the top, you see the safety pin. At the bottom, you can see the foot inside a shoe. You see the nails of the shoe, the places for the laces. The laces you don't see, but the metal there, that depicts very nicely. So X-rays were actually used very artistically to depict objects. And in the 50s, the shoemakers, they were actually so excited about X-rays imaging that in most shoe stores, you could actually put your foot in the shoe that you were about to buy into an X-ray machine and see whether your foot fits into the shoe. So you could actually see your toes, etc. This was very exciting. People were very excited. Of course, with the years, they started to become concerned about the use of X-rays and the health issues, as we will discuss next week, the health considerations. So this was not the ideal use of X-rays, but nonetheless very popular at the time. Now we'll talk about the basis of X-ray imaging, and actually X-ray imaging is nothing but a part of the electromagnetic spectrum. And here is a display of the magnetic spectrum. We have wavelength, electron volts, that is a unit that is frequently used. We will be using here for the first part of the lecture, and the frequency of the different objects. We have the wavelength, the representation of objects with the wavelength, and the frequency here, and the energy of the photons that are involved. We have, on the low range, we have ultrasound imaging. We have discussed that already today. We have magnetic resonance imaging, also working in the low frequency, low wavelength, long wavelength regime. We have medical X-rays, they are in this area here, and we have positron emission tomography at the high end of the photon energies, that is short wavelengths, that are over here. So you can see the techniques that we're discussing here in this course range from relatively long wavelengths, ultrasound, to very short wavelengths and high photon energies for positron emission tomography. Now, I want to introduce here some very important relationships that are useful. So we have the wave equation, that is the wave speed of light, 3 × 10⁸ meters per second, is equal to the wavelength times the frequency. We have the energy of the photon, which is equals to h nu, h being Planck's constant, nu the frequency. H is given in joule second, that's the value of h. We can express this in kiloelectron volts as 4 times 10 to the minus 18 kiloelectron volt seconds. An electron volt is essentially the the energy of an electron acquired in a electric field of 1 volt. We can re-express the energy of the photon as the Planck's constant times the speed of light divided by the wavelength. And if we express the wavelength in nanometers and the energy in kiloelectron volts, then this is easy to remember. This is 1.2 kiloelectron volts per nanometer. So if we have a wavelength of 1 nanometer, then we have 1.2 kiloelectron volts of energy. So now we're looking at the interaction of electromagnetic radiation with tissue. So matter here, but we'll basically talk about the interaction with matter. What are the elements that we have in matter that electromagnetic radiation can interact? And this is basically, we've got the nucleus and we've got the electrons. Now in imaging, we are mainly concerned with the interaction between X-rays and electrons. And here it's very useful to look at the structure of the atom. We know very well that the electrons have a binding energy that is associated to where they are in the molecule. So we have the K shell, which is here at the bottom. Binding energy for tungsten here is about minus 70 kilo electron volts. So this is the strongest binding energy here, and then we have different levels at which the electrons can be bound. They are discrete levels that comes from quantum mechanics. This makes sense because the binding energy decreases with shell distance. This makes sense. So we have the M shell here, which is minus 2.5 kilo electron volts. It decreases with shell distance, and we can make relationship to the Coulomb interaction. The nucleus is positive, the electron is negative, so it's attracted to the nucleus. The further away it is, it decreases with 1 over r squared, so we have a decrease with the shell distance relative to the nucleus. If we take hydrogen here, the K shell binding energy is now only 13 electron volts, so it's much lower. This is the closest an electron can be to the nucleus. It's in the K shell, so the binding energy increases with Z, that is the number of protons in the atom. So why does this increase with Z? This is again with Coulomb. The interaction, that is the force, increases with the electrical charge. It's multiplication of the two electrical charges. The electron is always one electron charge, and the positive charge is the number of protons that is proportional to Z. So it increases with Z. That also makes, just from a classical consideration, makes perfect sense. So if we now look at the lowest K shell binding energy that we have out there in the periodic table of elements, the lowest energy K shell binding energy that we have is for the hydrogen atom. It is 13.6 electron volts. And here we make an important classification. If the photon energy, h times nu, is bigger than the K shell binding energy for the hydrogen, then we consider the radiation as ionizing, and if it's below that, the radiation is non-ionizing. Ionizing means that the photon has sufficient energy that it is able to bump the electron out of the K shell and therefore produce a charged atom, and therefore therefore arises the term ionizing. So the take-home message here is that the ionizing radiation is for photons whose energy is above 13.6 electron volt. Here are some additional useful constants. We have the mass of the electron, the charge of the electron, and the rest energy of the electron, that is from Einstein's famous equation mc squared. The energy of an electron is equals to 511 kiloelectron volts. These are some constants that are useful for the problem sets of this course, and for addressing some quantitative questions, we'll reuse some of those values later on in weeks to come. So where does ionizing radiation occur? What is typically considered ionizing radiation? Here we retake the electromagnetic spectrum, the whole range here, from microwave to gamma rays. PET imaging is here. And this is the 13.6 electron volt. Here we have the energy. This is 10 electron volts. This is 100 electron volts. It's a logarithmic scale. This is where 13.6 electron volts is. The separation, that's the distinction. Everything to the right is considered ionizing, and everything to the left is considered non-ionizing. Now, if we look at where the separation is, we see it is in the ultraviolet range. The visible light, what we see here, is here. This is the light where we see the rainbows. So it's actually quite close to visible light, slightly above. And this is where why we use products like this one. This is typical for Switzerland. Sunscreen. We use sunscreen to block out the harmful ultraviolet rays, which have sufficient energy so that they can start to be ionizing in our skin. And when they are ionizing, as we will see next week, they can produce harmful effects in the body and ultimately cancer. So this is important why we carry sunscreen when we go outside, to protect ourselves from these effects. It's not just against sunburn, but also from a standpoint of health. So this is the use of sunscreen, blocking out the bad ultraviolet. So in summary, we are going to talk about ionizing modalities for the next few weeks. We have X-rays, scintigraphy, we're not going to talk about this too much, computed tomography in 2 weeks, mammography, angiography, PET, SPECT and CT, and the separation that is done between, when we consider this ionizing, is that we are using photon energies that are sufficient that they can dislodge an electron in the hydrogen atom. Here's the nucleus, the proton, here's the electron in the K shell, and the neutral hydrogen atom becomes positively charged upon the interaction with a X-ray.